So thank you everyone and good afternoon. What I'm going to present today is science-driven infrastructure that we are developing in a group. Mostly it started by the idea that we could calculate atomic properties very precisely. So we should have a common platform where we can compare different methods and different techniques of calculating these atomic properties. And then eventually we also realized that keeping the current scenario in mind of quantum era, maybe we should also integrate Rydberg atoms to the package. So the group at Guru Nanak Dev University, we are theoretical atomic physics group. And we are kind of versatile in doing a lot of work related to atomic structure, where these atomic properties are of applications. Like, for example, we can use our atomic properties in calculating spectroscopic data for astrophysical applications. We have also worked with quantum sensor, like in the first talk where Sanjukta talked about quantum sensors. We also proposed a quantum sensors using rubidium and cesium atom using EITs, and also quantum sensors for searching the permanent dipole moment for francium atom. And a small part of my work also relates to working with Rydberg atoms, and we are working in collaboration with the experimentalist group at GNDU to build better portable gas sensors. Also trying to move towards quantum foundation and calculate dispersion interactions between atom-atom, atom walls, atom nanostructures, etc. But major part of my research work is related to cold atom traps and atomic clocks, where we try to state insensitively trap atoms, like propose magic wavelengths for various atomic systems and ionic systems, and calculate systematic shifts for atomic clocks, and also propose various elements which might be used for building these atomic and optical clocks. So for sure, I cannot talk about all these projects which are being done in my group. What I'm going to present today is that we realized that as atomic physicists, we can calculate these atomic properties. And I said that we wanted to build a common platform which could be driven by scientific community and is user-friendly and could be used even by startups and experimentalists. So the work which I'm going to show has been done not at GNDU, but at Perimeter over a very brief period of time. So it didn't take a lot of time for us to build. And the credit goes to Vipul, who is my PhD scholar, and he was an international visiting graduate student at U Waterloo at that time. So as atomic physicist, we know that high precision atomic structure calculations, they play a very important role when we talk about developing technologies and also probing fundamental physics. The goal very naively is to solve wave equation, get precise wave functions, calculate properties, and use these properties for various applications and also for fundamental physics. And most of these applications have been talked about in various talks in this conference. We as atomic physicists are interested mostly in properties like energies, electric dipole matrix elements, polarizabilities, lifetimes oscillator strength, so on and so forth. So the idea is to solve the wave equation, which could be a Schrodinger equation or a Dirac equation, depending on your requirement, like you need non-relativistic results or you want relativistic results. And it's not always possible to solve these wave equations exactly. So what we try to do is we try to achieve close to exact, if not exact results using various methods. For example, this table here shows the helium atom ground state energy calculated using various methods. The real challenge in solving these wave equations is the electron-electron repulsion term present in the Hamiltonian. So if I ignore that electronic repulsion term, then the energy calculated is around 38% off by the experimental values which we get. And these inter-electronic repulsion can be included perturbatively, and if we do perturbation up to the order of 13, then we see that the results, theoretical results, they match up to 0.01% when compared to the experimental value. But perturbation theory is not always feasible, especially for heavier atoms. So people look for methods which are not as precise as perturbation theory, but they are computationally efficient, and then they give us results decently well The problem is that such methods like the Hartree-Fock method, we are able to calculate the results to a reliable precision, but there are missing correlations. So what we do as atomic physicists is that beyond the Hartree-Fock approximation, the missing correlations are calculated using post-Hartree-Fock methods. So the present status in the atomic physics community is that a number of atomic physics groups, they are using various methods to calculate these atomic properties. Some use relativistic methods, some use non-relativistic methods, some even use semi-classical calculations, some use precise high accuracy many-body perturbation theory or configuration interaction methods, and so on and so forth. And a few of these packages or softwares are concentrated on just calculating atomic properties for Rydberg states. For example, the alkali Rydberg calculator is very popular when it comes to calculating Rydberg atom properties. So the landscape is fragmented. A lot of people use a lot of methods to calculate these atomic properties. The problem is most of these codes are really, really very old. They are written in Fortran. They're outdated, although a new version keeps coming up every few years, but too many updates by different people makes things very complex to maintain, and sometimes they are really poorly documented. So you don't have clear instructions how to do it. You first have to install it, compile it, and so on and so forth. One main problem with these codes is that almost all of them, they don't give an accuracy estimate. So I think that it doesn't serve the purpose of the present community where the demand of atomic data is so much. And in addition to that, within one particular method, we observed that the techniques are scattered. The theoretical techniques used to calculate atomic properties scattered. So what happens is that the decades of development and refinement of these theoretical techniques have led to this fragmentation in atomic physics community. What happens is, even though several groups are using same method to calculate atomic properties, but they are using different computational techniques, their results for few properties, they don't match. So there's a mismatch, and each group kind of claims that their result is better than the other. So what we try to do here is that we try to see the role of computational techniques as well as methods in calculating various atomic properties. So based on this observation that we need a lot of atomic data, and there are barriers to access these atomic data because there's a high threshold to first download these complex codes. They have unsupported documentation, and most of them, they require expert knowledge to run them. So based on this observation, we propose that, okay, we are theoretical atomic physicists. We already have a number of methods in our group already developed. So why not bring it on a common platform, which can be used by experimentalists and also startups. So the goal here is to build a unified community cyber infrastructure for various applications. And there are three main objectives. So it's kind of proposal, which is work in progress, but I'll show you what we have developed so far. The first objective is to evaluate atomic properties using various theoretical methods, and also within a method, compare different computational techniques to identify which is the most optimal technique to use for our calculations, and also integrate Rydberg properties within that platform. And also on the way, we plan to develop new methodologies by combining our ab initio atomic physics calculations with experimental results and perhaps with machine learning as well, so that we can develop advanced atomic structure calculations. Main objective goal with which we started the project was that we wanted to build this infrastructure that it is user-friendly, has relativistic programs in it for high quality quantum and atomic data. So currently, we have atomic physics package running. We can calculate properties for various monovalent neutral atoms. We want to extend it to highly charged ions, which we know how to do that. And present status is we are trying to integrate Rydberg state as well in the platform. The methods which we are currently using are Hartree-Fock method, which I'll discuss briefly in coming slides. And we use two different techniques to do these calculations. And then we also have a bridge where we use post-Hartree-Fock method, the all-order method, to calculate properties for ground and a few excited states where high precision is required. For Rydberg states, we currently have a module which is not integrated in the platform right now, but it can do calculations using model potential for Rydberg atoms. So I won't sell it by saying that it's a very innovative work or something. The idea of the reason why I wanted to present an unfinished work here was that I wanted to have feedback from the Rydberg atom or atomic physics community in what direction we should actually move to build this platform. But our idea was that we want to make it usable and accessible so that it requires minimum computing knowledge. And by that, what I mean is that you just supply a few parameters which describes your request, and you get the output in your required format. Obviously, we want it to be collaborative in nature. We welcome feedback and requests from experimentalists and for theoreticians. Like if experimentalists want some additional property to be integrated in the platform, then they can always put a request and we can try to add a module to that platform. And one main idea was that we think that it will benefit non-research organizations and startups which don't have close collaboration with the research community. So they always have to collaborate with some theoretical groups for these atomic data. Since we want to make it open access, I think it should help people who are not closely knit with the research community. And as atomic physicists, so this is something which is like computational scientist part. As atomic physicists, we also want to explore new ways of combining experimental data and machine learning to build better algorithms and use optimization techniques in terms of scaling our calculations with respect to time and the problem size. Okay, so this is the workflow, which is divided into 3 layers, the input layer and the output layer. It will be supported, it is supported by a graphical user interface. And the middle part is the computational engine, where you can use methods and various techniques to do the calculations. So what I'm going to discuss today is mostly the upper part of the flowchart, which has been completed and it's running, but not made public. And I request more feedback for integrating the Rydberg atom from the community. So the method which we use currently for our atomic structure calculations is, as I said, we start with the Hartree-Fock approximation. And in Hartree-Fock approximation, the goal is to solve the Dirac wave equation, where the many-body Hamiltonian is represented by this equation here. This is the 1-electron Dirac Hamiltonian. As I mentioned previously, the real challenge is to calculate or solve the wave equation when this inter-electronic repulsion is included in the Hamiltonian. And people use perturbative methods, which is not very efficient, especially for systems having large number of electrons. So what we do instead, we use Dirac-Hartree-Fock approximation. It's an independent particle approximation. It's a central field model and a variational principle. It's self-consistent. And in that approximation, what we do is we try to use a Hartree-Fock potential instead of this inter-electronic repulsion, which I'll show in my coming slides. So in Dirac-Hartree-Fock method, the electrons are assumed to move independently. So it's an independent particle approximation. So they are assumed to move independently of each other in average potential due to the nucleus and other electrons. And it's one of the most successful methods when it comes to reducing the computational efficiency in producing atomic structure calculations. In independent particle approximation, the complete wave function is represented by Slater determinant of independent orbitals. And for relativistic case, these independent orbitals are Dirac orbitals. What we do is we solve for the single particle radial wave function part of the Dirac orbital by substituting it in the Dirac-Hartree-Fock equation written here. And we solve for the 2-component Dirac orbital, where P and Q are the upper and the lower components. Now, this is the Dirac-Hartree-Fock potential, which we substitute in our Hartree-Fock equation. And it consists of 2 parts, the direct part and the exchange part. So direct part is it has a classical analog. It kind of represents the electron-electron Coulombic interaction, and the exchange part doesn't have a quantum, it doesn't have a classical analog because it appears due to the fact that electrons are indistinguishable fermions, and it's more trickier to handle the exchange part, and direct part is not so computationally tricky to handle. Okay, now there are two different methods which are integrated in the package right now. We solve the Dirac equation using finite difference method and also using basis function method. Briefly, we use Adams-Moulton integration to do these finite difference calculations. It's a k plus 1 point integration method. We start with an initial guess, and then we keep changing this initial guess so that the correct number of nodes, correct energy, and correct behavior at 0 and infinity can be found. So we can generate number of states using finite difference method, but this finite difference method would always give us wave functions which have positive values of negative values of energy. So they always produce bound state wave functions. But if we want to use the output of our Dirac-Hartrott wave equation as an ansatz for our post-Hartrott, what we want is in addition to having these negative energy, these bound state solutions, we also need continuum solutions in our ansatz. So instead of doing the finite difference technique, which is good technique when it comes to calculating properties for bound states, we use something called basis function method, and it's a very efficient and reliable method to solve differential equations, where we expand the radial part of the wave function in terms of basis functions. And once we substitute this in our Dirac equation, written in a very compact form here, it yields a generalized eigenvalue problem, which can be solved by using normal linear algebra methods. So right now, the platform has a provision of comparing two types of orbitals. We also have a module written for the Slater type orbitals, which haven't been integrated, because these are the two most popularly used basis function in atomic physics community, the GTOs and the B sublines. Briefly, GTOs are Gaussian type orbitals where you write the basis function, expand the basis function in this Gaussian form, and it gives very reliable, accurate atomic properties, especially for properties where the wave function is sensitive to the nucleus. So as you see here, the Gaussian type orbitals have a dense distribution close to the nucleus, but the distribution is not so dense as you go far away from the nucleus. So in order to have an optimally distributed Gaussian set, what we also integrated in the infrastructure was that we tried to build an adaptive basis set. So what happens is this Gaussian type orbitals which are used in literature are called even tempered bases, because the parameter alpha, which is used in the Gaussian function, is chosen to be a geometric progression. And the parameters alpha naught and beta are chosen out of experience, like depending on the system you're working on and the property you want to calculate, you choose these alpha naughts and betas. And if you choose very different or very incorrect parameters, you'll definitely get incorrect values for your atomic properties. So that was the problem. We realized that if we are trying to build an infrastructure which is like user friendly, people don't need knowledge of atomic physics, etc., this is definitely a problem. You need a prior knowledge of choosing these parameters appropriately. So what we do in our adaptive basis set technique is that we offer more flexibility to these GTOs. We strategically select parameters so that the first and the last basis is fixed depending on what cavity radius you are using and how many number of basis sets you are using. And then the rest of the bases are produced on an exponential grid. So the advantage is that with this kind of adaptive type basis set, we were able to produce as many number of bases for Gaussians as possible. Currently, the limit which theoretical physicists they have is that they cannot produce beyond 40 basis set using GTOs, but we were able to produce like 70 GTOs as well using these techniques. Okay, so the other very popular basis set technique is the B-spline basis techniques, and it's more popular amongst the graphical designers rather than atomic physicists or quantum chemists. due to the fact that it offers more control over the function. And B subline of order k is represented on a knot sequence by these recursive relations. And as you can see, the distribution is much better than the Gaussian distributions, even away from the nucleus. Now, when we try to write our Dirac equation in terms of the basis set, which is finite, what we end up getting are some spurious states. These spurious states are non-physical states represented by these highly oscillating wave functions here, which should not actually be part of the energy spectrum. For example, in this table, you can see that these non-physical states corresponding to 1p half, 2d 3 half, and so on, they have energies which are incorrectly matching the physical states like 1s half, 2p 3 half, and so on. So these are unphysical, and they arise due to the fact that when we write our Dirac equation in terms of these basis set, when we expand our Dirac equation in terms of basis set expansion, the non-relativistic limit for our kinetic energy is not correct. So we definitely want to eliminate these non-physical states. And in literature, people use something called balanced basis set to remove these spurious states. And these balanced sets, they offer the correct relation between the upper and the lower components of the Dirac's radial wave function, which I discussed previously, so as to establish a correct behavior of the Dirac equation or the kinetic energy in the non-relativistic limit. So there are two kinds of balance conditions, the kinetic balance conditions, where lower component of the wave function is related to the upper component by following relation. And these kinetic balance conditions, they give the correct non-relativistic limit for the positive energy solutions of the Dirac equation. And if we use dual kinetic balance condition, then both upper and lower components are related to each other. And this gives the correct non-relativistic limit both for the negative and the positive energy solutions in our Dirac equation. And sometimes what also people do, especially when they're using B sublines, they don't use these balance conditions. They use something called MIT back conditions, where they move the non-spurious state from the start of the spectra at the end of the spectrum. And then when they are using the Dirac-Fock values as an ansatz for post-Dirac computation, they ignore the end of the spectra, which has the spurious state. But we think that it's more physical to remove these spectra because they are non-physical by using proper methods rather than just shifting them to the end of the spectrum. So we have integrated all these techniques in our platform. For the Gaussian type orbitals, we have the conventional GTOs, even tempered, which are used in literature. We have these adaptive type GTOs and also GTOs using dual kinetic balance conditions. For B sublines, we have these MIT back condition B sublines integrated in the platform. We can do calculations using B sublines with kinetic balance conditions and dual kinetic balance. So this is a comparison of various balance conditions where I try to show that it's very important to use proper balance conditions in order to remove the discrepancy which is existing in literature. For example, these are the values which were calculated using B suppline MIT bag model and GTOs even tempered, which exist in literature. And as you can see, for some states, there are discrepancies, although they are using same Hartree-Fock method. But since they are using different techniques, their results don't agree. However, if we use proper balancing conditions, that discrepancies can be removed. So a good debate can be actually we can come to a conclusion for a debate in scientific community. Also, there's a provision where we can find the optimum value of number of bases and the cavity radius you want to use for your calculations, so that you can choose the optimum value of these parameters. Like obviously, if you use more number of bases and a large cavity, you will get better results, but that's going to increase the computational efforts. So you want to use an optimal basis, and what we notice is that B sublines, it gives us reliable values even for smaller number of bases as compared to the GTOs. And not only that, some of the properties where the properties were dependent on the behavior of wave function close to the nucleus, we observed that GTOs were performing better than the B sublines. And beyond the Hartrop approximation, the missing correlations were included using all-order method. I'll briefly go through it because I want to leave more time for feedback. But what we do is we start with the Hartrop numbers which we have produced and then apply a excitation operator, which is in exponential form. And currently we are employing single double approximation where these excitation operators, they represent single and double excitations. We are using a linearized version, which means that in the expansion of this exponential, we are only using linearized version. And once we have these wave functions, we can calculate matrix elements. And we can also sometimes calculate the triples, contribution of triples perturbatively. And mostly these calculations are done so that we can give an error bar estimate in our results. These are the hyperfine constant values produced using all-order method using the package. And we notice that if we use GTO adaptives, then even using 40 number of bases, we could get results very close to experimental values. And in theory, in literature, the theoretical results have been produced using 70 B sublines. So the number of bases required could be reduced if we appropriately optimize our bases over the grid. The package also calculates polarizabilities for ground and various excited state. So coming back to the flow chart, I think this part of the program has been done, integrated, running. And what I'll describe in next 5 minutes is what we plan to do for the Rydberg atoms. Okay, so probably I don't need to talk about why Rydberg atoms are special. They are exotic atoms, they have tunable interactions and large polarizabilities, play important role in quantum computation. They are very sensitive, even sensitive that Rydberg interactions, they inhibit multiple excitations under appropriate conditions, which is the basic concept behind entanglement required to produce a 2-qubit gate. This is a Rydberg gate scheme. And using these Rydberg interactions, you can actually produce high fidelity quantum gates if you apply like controlled sequence of pulses on the atoms. Okay, so coming to the theory part, we are planning to use a model potential approach to do these calculations. But as compared to the other approaches, which also use model potential, they use model potential within the non-relativistic wave equation, the Schrodinger equation. But since we know how to handle relativistic Dirac equation, our proposal is to include the model potential in the Dirac equation. And instead of adding the relativistic corrections, which the other packages do, they add the relativistic corrections perturbatively to the Schrodinger equation. We are starting with the relativistic equation. So I don't think relativistic effects matter a lot for Rydberg atoms, but for like low-lying states, low-lying angular momentum states, these effects are appreciable. You see fine structure splitting in various atomic levels. But the main point is, since we know how to handle it very easily, we propose to use a model potential approach within the relativistic equation, relativistic Dirac equation. And this model potential, it captures the interaction between the valence electron and the ionic core. So in our approach, all we have to do is, instead of using the Hartrop potential here, we'll just substitute it with a model potential. And the parameters required for the model potential, usually people calculate them by using available energies. In our case, since we also have access to theoretical calculations, we can also use theoretical parameters wherever the experimental values are not available. So the idea is to use model potential on a relativistic equation and solve for the wave equation and like find number of properties for Rydberg atoms. And the current status for this part is that we have a module where we can solve this equation, calculate wave functions, but we are still writing codes to calculate various properties for Rydberg systems, and it's not yet integrated in the platform. So this is the interface, and maybe I can quickly show what it currently does. So this is the user interface where I can choose the grid value, cavity radius, number of grid points, and also choose number of bases where I can, like where I want to compare different bases for my atomic structure calculation. So I'll quickly run one of the systems, the cesium atom, and it takes about like 20 seconds to calculate. And meantime, I can show what properties have been integrated in the platform. So we can calculate dipole matrix elements, PNC matrix elements, amplitudes, hyperfine integrals right now. And after doing calculations at Hartree-Fock level, there's a provision to include the missing correlations using linear coupled cluster method. So you can calculate various properties at the post-Hartree-Fock level as well. Let me check if the code has already run, so it like takes it runs very quickly. It's cloud based, so you don't have to install any software in your code. For example, Arc requires you to install number of Python packages and modules on your local system. So I'll download the file. And then let's say I want to calculate the dipole matrix elements for cesium atom. So this is the output which was generated. And this is a 6s half, and let's say 6p3 half. And it quickly gives the dipole matrix element. And also the package gives a provision of checking if the cavity radius and number of bases you are using are enough for representing your wave function. For example, if I want to check, like if I want to calculate property for, let's say 6s half state, then I can generate a wave function form for my 6s and then see if it fits within the cavity radius or I need to increase the cavity radius and so on and so forth. Okay. So this is work in progress. Definitely the Rydberg system has to be integrated here. And I'm coming to the end of my talk, where I want to advertise another work which is being done by the researchers at University of Delaware, and I'm part of the team. It's a portal for high precision atomic data and computation, since a lot of experimentalists are working with cold atom physics. This is the version which is on, which is published, and it has almost atomic properties and also nuclear properties for 28 elements. Right now, we are working on building creating a next version of the portal where we have included even divalent system and highly charged ions. And I think I heard a number of talks where people were doing experiment with strontium, so maybe they would be of useful. And the polarizability module, it also gives you the magic wavelength and tune out wavelengths for doing these cold atom trappings. So with this, I think I would like to end, and I would really genuinely ask for feedback where you think that the program should go in that direction. So thank you so much.
We have time for some questions.
Very nice. One question, what is the difference between the one in Delaware and the one that you show? Is the same type of methods, approach to compute? Or?
Yes, they are also doing the post-Hartree-Fock calculations, but it's a static version right now. Like you cannot do computations as per your requirements. So the data is, maybe I can show you the website. So it's with Mariana, and yeah. So this is the version which is live, and this is the version which we are working on, which is not like live right now, but so the data is available and it's ready to be downloaded. Like you can download it in CSV form or any other form. So it's not like the package idea where you give the input as per your requirement. It's not like a dynamic portal. But I think, yes, but I think Mariana is also planning to publish the parallel version of, this is where I also contributed, parallel version of these codes, which can be which are open access and can be downloaded and used by people.
Further questions? Okay, if not, let's thank all the speakers in this session for very nice talks, and we conclude the session.